Welcome back to linear algebra. In this video, I want to look at abstract vector spaces. This is an idea I've hinted at several times earlier in the course, where we're going to take the idea of a vector and generalize it so that it's not restricted just to the Euclidean vectors and their geometry, but to any number of different structures that follow similar patterns. One of the most important applications is going to be showing that functions can behave as vectors, and we can define a vector space on functions. We're going to look at that in this video, but not exclusively at that vector space. Let me get my head out of the way, and let's start with the formal definition, most of which should be familiar to you. A vector space is a set coupled with two operations. Vector addition, so we have u plus v as the notation. Scalar multiplication, we have k times v as the notation. And we have 10 properties here, which we're going to be looking at. First 5 properties, we want V to be closed under vector addition. Symbolically, for all U and V in set V, it must be the case that the sum U plus V is also in set V. Vector addition is commutative. For all U and V in set V, U plus V is equal to V plus U. That's not a U. That looks a little bit more like a U. Associative, U plus V plus W is equal to U plus V plus W. There's a zero vector, and the zero vector has to have the property that V plus 0 is equal to V, and there has to be an inverse, so that V plus the inverse of V is equal to 0. Then, a few more properties that don't all fit on the screen at once. And the last 5 properties here. V is closed under scalar multiplication. So for all vectors and for all scalars k in the real numbers, k times V is in set V. Now is probably a good time for me to mention that in general, this set does not have to be the real numbers. Vectors defined over the integers are an interesting idea in themselves. Vectors defined on the complex numbers are an interesting idea in themselves. But for the sake of time and the sake of convenience, we are only going to look at vectors defined on the real numbers in this course this semester. Right. Scalar multiplication distributes over vector addition. So if you have some scalar k and the sum u plus v, you get ku plus v, no, kv. Scalar multiplication distributes over addition in the reals. So if you have adding two scalars, k plus l times v, you get kv plus lv. Scalar multiplication associates with multiplication in the reals. So if you have k times lv, or you have k times l times v, it's the same thing. And the last property tells us that for real number 1 as our scalar, 1 times the vector v is itself. These 10 properties are the definition of a vector space. Any set which you can couple with two operations so that it satisfies all 10 of these properties is itself a vector space. As I said at the beginning, these properties should look familiar. If you go back to the very beginning of this course, when I introduced you to the Euclidean vectors, one of the first things we did was prove that the Euclidean vectors satisfy all 10 of these properties. In this video, I want to introduce you to a different set, the set of polynomials, which are going to also satisfy these 10 properties. I won't prove all of them because that would take quite a bit of time, but I'll prove a couple to give you the general idea and hopefully give you a picture of why this is going to work. The polynomial vector space is denoted as P sub n, and it's the set a naught plus a1 plus a2x squared, a3x cubed. You keep going until you get to an x to the n, where all of those coefficients, a naught, a1, a2, all the way down to an, are real numbers. One of the first things I want to stress about this polynomial space is that I'm often going to refer to it as polynomials of degree n. But the name here is slightly different from what you've probably seen in the past as the description of polynomials. A polynomial of degree n, we always insist that that lead coefficient, the thing being multiplied by x to the n, has to be non-zero. Because you could keep going essentially forever, right? A linear polynomial, something like ax plus b. You can add 0x squared, 0x cubed, 0x to the fourth, 0x to the 2,000, 0x to the 5,768,943, and so on. And it's not useful when you are analyzing a polynomial to be able to keep going and say that the polynomial has all of these degrees. And we name it based on the smallest degree that it carries. Here, we actually have to look at things slightly differently. It's going to turn out that giving a cap, giving a maximum degree, is the structure that is needed in order to have a vector space. So Pn, I'm going to call the polynomials of degree n, but compared to how you've used the word degree in the past, this is the polynomials of degree n or smaller. So if, for example, in P3, the polynomials of degree 3, well, sure, I have something like x cubed plus 5x squared plus 6x plus 9. That is very clearly a third degree polynomial, so it definitely belongs in P3. X squared plus 4x plus 4 is also a polynomial in P3. You would call this a second degree polynomial, but for the purposes of linear algebra, we can accept it as a third degree polynomial because we really mean degree 3 or smaller whenever we say third degree. And the reason that this is so very important is 0. The constant numbers are degree 0 polynomials, except for 0 itself, which is an undefined degree of a polynomial. But we're still going to say it's okay, it's degree 3 or smaller, so it's in Pn. And that's important because one of the properties of vector spaces requires us to have a zero vector, which in this case means a zero polynomial. So I claim that Pn makes a vector space for any constant n, and I want to prove this in general. I want to prove it for any constant n instead of taking a particular one, which means that we're going to have a bit of a mess on our hands in keeping everything straight, but I think it'll work out okay. All right, I'm going to need, um, excuse me, I'm going to need three different polynomials. F of x, I'm going to define using a's, a naught plus a1x plus all the way down to an x to the n. G of x is going to be the polynomial of b's, so b naught plus b1x plus all the way down to bn x to the n. And polynomial h of x is going to be the c's, c naught plus c1x plus all the way down to cn x to the n. I'm also going to need a couple of constants other than a, b, c, f, g, and h. So I guess I'll use k and l. And one by one. The first property is closure. So we want to look at f plus g, right? Using the customary definition of adding two functions, f plus g is this sum. And we know that we can rearrange this. We can use the commutative and associative properties of the real numbers. And since the real numbers are closed on addition, a naught plus b naught is a real number, a1 plus b1 is a real number, an plus bn is a real number. And again, we're not worrying about the zero vector. So, excuse me. So I don't have to worry about an plus bn equals 0 because polynomials of degree n or smaller are all in Pn, so everything works out fine. All right. Second property, we ask for commutative. I'm going to skip over that one for the time being. It's not that interesting, and we'll get enough ideas out of this if I jump straight to associative. The associative property asks me to look at f plus g plus h. Which is not that difficult to deal with, but kind of lengthy, so it doesn't quite fit on the page. But I can definitely use the commutative and associative properties to rewrite this summation without the parentheses. And I can use the commutative and associative properties of addition on real numbers to put parentheses back in. before realizing that what I just did was rearrange this to get my polynomial f outside of the brackets and g plus h inside of the brackets. For my zero vector, I'm going to use the null polynomial. I'll use a script letter O to represent it so it looks different from a zero, but O of x is the null polynomial, the zero polynomial. And f plus null is equal to a naught plus a1x plus etc. down to an x to the n plus 0, and adding 0 to something doesn't change it. So I really have the function f that I started with. The fifth property asks about inverses. That's something that I'm going to ask you to look at later. The sixth property is closure in the scalar multiplication. So if we take our scalar k times our function f, we get k times a naught plus a1x plus all the way down to an x to the n, and I can use the distributive property of the real numbers to write this as k times a naught plus k times a1 times x plus all the way down to k times an times x to the n. And since the real numbers are closed on multiplication, k times a naught, k times a1, all the way down to k times an are in fact all real numbers. So that makes this a polynomial. It's in Pn. Right. I'm kind of glossing over that, but I want to take a moment now while I'm thinking about it and talk about that a little bit more. This isn't a guarantee, and it is something that comes from our definition. Imagine that I change the definition of Pn ever so slightly. And I say that instead of taking real number coefficients, I want the polynomials with integer coefficients. Well, every polynomial you've ever really worked with has had integer coefficients with very few exceptions. But if I insisted that the coefficients were all integers, this wouldn't work anymore. Because even if a naught, a1, all the way down to an are integers, k is still a real number. So I could define k to be the square root of 2. And the square root of 2 times an integer is no longer an integer. Right? So I wanted to at least address that briefly, how fragile this definition is, how close to a knife edge we are, and how easy it is to have a space that looks kind of like it should behave as a vector space, all of a sudden falls apart if you aren't paying attention. So you do have to take your time, you have to be careful, and you have to verify that all of these things actually do work. Continuing our journey here, I'm going to skip over 7. That's another one that I'm going to ask you to look at. Multiplication distributes over polynomial addition. I am going to look and show that scalar multiplication distributes over addition of the real numbers. So if I have k times L times F, that is k times L. I'm sorry, I'm looking at the wrong one. This is k plus L times F is equal to k plus L times a naught plus a1x plus all the way down to an x to the n. And we can distribute the multiplication here, k times a naught plus a1x plus all the way down to an x to the n plus L times a naught plus a1x plus all the way down to an x to the n, which is exactly k times f plus L times f, and we are happy. All right, I started looking at 9. I'm not going to. I think I've spent enough time looking at all these proofs. Let's skip over 9 and 10 as well. Right, 9 is associativity between scalar multiplication and multiplying scalars. That's the k times L times f that I started to write out. And so on from there. So again, technically not a complete proof because I skipped over about half of the properties, but I hope that gives you a good picture of what this proof is supposed to look like, and you can kind of fill in the blanks on your own if you are curious. A couple of these are going to actually show up in homework. I'm going to ask you to prove some of these properties for yourself, verify that they do in fact work. But for today, instead, I want to talk a little bit about why we care about abstract vector spaces. First of all, why do we care about polynomials of degree n? And the answer to that is that honestly, we don't. It's just a convenient stopping point. You should remember from your study of calculus the idea of Taylor and Maclaurin series, or if you haven't quite gotten that far in calculus, you'll get there soon. None of the calculations matter. All that matters is the end result, which is that if you take an infinite degree polynomial, you can use that as a way of representing any differentiable function. And so if we take the limit here as n goes to infinity, this vector space is the vector space of all differentiable functions. If you're interested in studying it in detail, that idea is known as Hilbert space. It's one of the fundamental ideas in quantum mechanics, and the mathematical study of Hilbert space and things related to Hilbert space is known as functional analysis. So a couple of interesting things that you may continue on to at some point in the future. For our purposes right now, we're going to stick to finite degree polynomials. A little bit later on, next video or the one after it, we're going to talk about the dimensions of abstract vector spaces, and finite dimensional vector spaces are something that we are going to have the tools to work with in this course. Infinite dimensional vector spaces are not. And so if we exclude the go on to infinity and use this as an approximation of all differentiable functions instead of as exactly all differentiable functions, it takes it from something we don't have the tools to work with to something we will be able to work with within the scope of this course. So just a little bit of convenience of notation there. More generally, though, the reason that we care about saying that anything is a vector space is that once we have something as a vector space, all of the properties of vector space come with it. So as a quick example, near the beginning of the course when we were talking about the properties of the Euclidean vector spaces, if we take any abstract vector space V, any one vector in V, and any constant R, zero times V is the zero vector. Any constant times the zero vector is the zero vector. The constant -1 times our vector is the inverse of that vector, and the zero product rule. If k times v is equal to 0, then k equals 0, or v is the 0 vector, or possibly both. We proved this as a property of Euclidean vector spaces. That proof can carry and very naturally allow us to prove the same thing for any abstract vector space. So as soon as you show that a set you're working with satisfies those 10 properties of vector spaces, you get 4 extra properties for free, no extra charge. The last thing I want to do today is look at one other vector space. This is kind of off the wall as vector spaces go, which is one of the reasons I like it so much. So if I take the vector space of real numbers and I set up vectors of u and v, which are defined by the real numbers a and b, and I'm going to define the operations u plus v is equal to a times b, and k times u is equal to a raised to the k power. So our vector addition means multiplying, and our scalar multiplication means exponents. And I claim that this forms a vector space. In order to prove that, I'd need to go through all 10 of those properties. And for the sake of time, I don't want to, and I don't necessarily want you to either. I would like you to show that V is closed under both vector addition and scalar multiplication. I'd like you to identify the 0 vector and verify its properties. And I would like you to verify the properties of 1. Right, so that's 4 of the 10 properties of a vector space. Those are the only ones I'm asking you to look at here. It's a little bit faster than looking at all 10. It's not that bad. It's a little bit weird to wrap your head around. Addition means multiplication, multiplication means exponents. But if you take a little bit of time and you play around with it, it should start to make sense. And more importantly, once it makes sense, a lot of what we're going to be doing is going to become a lot more natural to you. So take a couple of minutes, see what you can do with that, and I'll see you in the next video.